Hello everyone. Today we are going to analyze this propped cantilever beam. In this beam, there is uniformly varying load. It varies from 0 in the point A to W in the center and again to 0 in the point B. The span of the beam is given as L. To analyze this beam, we are going to use consistent deformation method. Now let us find the degree of static indeterminacy. In this beam, the number of unknown reactions and moments are 3. The available equilibrium equations are 2. The degree of static indeterminacy is equal to 3 minus 2. We will get 1. From the point A, let us release MA. Right now, in the point A, there is a fixed support. But when we release MA, it becomes a hinged support. Previously, this beam was a propped cantilever beam, but now it is a simply supported beam. Using this formula, we can find MA. We can take delta on the other side. It will come in the denominator. We know that P is MA. In the point A, there is no rotation, so delta will be 0. Delta L is the displacement due to the loads. Here the displacement is the slope. If in the simply supported beam there is uniformly varying load acting in this way, the formula to find the slope in the point A is minus 5 WL cube upon 192 EI. We have found delta L. Now we are going to find delta, that is the slope due to the unit movement. We have to remove all of the loads from the beam and to apply unit movement in the point A. You can see that I have removed all of the loads and applied unit movement. I have applied unit movement in the anticlockwise direction because MA will be acting in the anticlockwise direction. Now let us find delta, that is the slope in the point A due to the unit movement. If in the simply supported beam there is a movement in the point A, the formula to find theta A is WL upon 3 EI. Here W is 1, so it will be L upon 3 EI. We have found delta L and delta. Let us apply both of them. Negative into negative, it will become positive. We can take L upon 3 inversely and then multiply. We can eliminate L. Here it will be L square. Then we can eliminate 3. Here it will be 64. Finally, for MA, we will get the expression as 5WL square upon 64. Now from the point A, let us take a moment about B and find RA. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. RA is acting in the clockwise direction, so that it will be positive and the distance is L. MA is acting in the anti-clockwise direction, so that it will be negative. The uniformly varying load is acting in the anti-clockwise direction, so that it will be negative. For the UVL, we have to multiply the area with the centroid distance. We know the area formula of a triangle, that is half into BH. Here the breadth is L and the height is W. Now let us find the centroid distance. We know that it is a symmetrical triangle. The centroid lies in the center. When we divide the length L by 2, we will get the centroid. We can take this term on the other side. It will come as positive. 2 into 2, it will be 4. L into L, it will be L square. We can add these two terms so that we will get this. Then we can eliminate L and square. Finally, for RA, we will get 21 WL upon 64. Now let us apply the rule sigma V is equal to 0. and find RB. RA and RB are acting upwards, so both of them are positive. The UVL is acting downwards, so that it will be negative. For the UVL, the area is the total load. Finally, for RB, we will get 11 WL upon 64. Using the right hand side rule, we can find the shear force values in the point A, and using left hand side rule, we can find the shear force values in the point B. Here you can see the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment. We can make a section in this point and find the distance. You can see that in that point, I have made a section at a distance of x from the point B. We have to find this height. For the distance of L upon 2, the height is W. So for L upon 2, it is W. But we need the height at the distance of x. So we have to multiply with the x. In this way, we will get this height as 2Wx upon L. We know that in this section, the shear force is 0. Using left hand side rule, we can find the shear force. We know that in the left hand side rule, upwards will be negative and downwards will be positive. RB is acting upwards, so that it will be negative. The UVL is acting downwards, so that it will be positive. For the UVL, the shear force is the area. Let us take this triangle. We know the area formula of a triangle, half into BH. Here the breadth is x and the height is 2Wx upon L. We can take this term on the other side, so it will come as positive. Then we can eliminate W. Also we can eliminate 2. X into x, it will be x square. L into L, it will be L square. Then we can take root on both the sides. In this way we can get x, which is equal to L root 11 upon 8. In this expression, instead of x, we can apply this. We can eliminate this L and this L. We can eliminate 2. Here it will be 4. So for the height, we will get a new expression, root 11 upon 4W. Now from the point B, we are going to find the maximum positive bending moment. In this case, we have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. RB is acting in the anti-clockwise direction, so that it will be positive, and the distance is L root 11 upon 8. The UVL is acting in the clockwise direction, so that it will be negative. For the UVL, we have to multiply the area with the centroid distance. We know the area formula of a triangle, half into BH. For this triangle, this is the breadth and this is the height. So this is the area, and the formula to find the centroid distance towards the left is 1 upon 3 into B. So 1 upon 3 into L root 11 upon 8. After the simplification, for the maximum positive bending moment, we will get 11 WL square root 11 upon 768. We know that in the point B, the bending moment is 0. Now using the right hand side rule, we can find the bending moment in the point A. In the point A, we have MA, which is acting in the anti-clockwise direction, so that it will be negative. Here you can see the bending moment diagram. Now we are going to end this session. Thank you for watching this video.